Good day! Welcome to Physics 1510, Chapter 10. This is going to be the first of 3 chapters that talk about various heat and thermodynamics topics. This particular chapter, we're going to focus primarily on temperature. What temperature is, changing between temperature scales, the ways in which we measure it, and some various things that change directly related to an object's temperature. Next couple chapters, we will expand that to talk about thermal energy and various processes related to thermal energy. But for right now, we're just going to start with temperature because temperature is the first and easiest way to get any sort of an estimate on how much thermal energy is in an object. So let's go ahead and get started. Now, for these 3 chapters, thermal energy is going to be the main thing that we are talking about, and the conversation is gonna go a lot of different ways. We need to start by at least briefly discussing what thermal energy is. And it is a form of energy, like all the other forms of energy that you've studied across all of your other science classes. And as a form of energy, according to the laws of thermodynamics, energy cannot be created or destroyed, but it can take on many different forms, and it can change what object possesses it. You can never detect energy directly itself. You can only ever see what energy is doing. For example, when electrical energy passes through a light bulb, you don't see the energy itself, you just see the light given off by the gas in the light bulb when it has energy. So, not detecting the energy, just detecting what an object with energy is doing because it has energy. This is true of all energy forms, and in Physics 1500, the previous physics class, that class mostly talked about mechanical forms of energy. The 3 listed here being the most common ones: kinetic energy, gravitational potential energy, and elastic potential energy. These are all mechanical forms because they're already in a form to do mechanical work in 3-dimensional space. They move things around or they represent motion. Thermal energy is going to be the first non-mechanical form that we talk about in this class. And thermal energy is not considered a mechanical form of energy because it by itself inherently isn't really doing anything. It's really hard to get thermal energy to do work for you. It doesn't really accomplish a whole lot. When an object possesses thermal energy, all that energy really does is just make it hotter. That in and of itself isn't really doing much for you. So it's not accomplishing mechanical work by itself, so it's considered a non-mechanical form of energy. But like all the other forms of energy, we're going to measure it in joules. It can transfer between different objects. We're going to talk about that in a minute. And I lose my train of thought a lot. Pardon me for a second. And it can change what form it is in. Frequently, mechanical forms of energy, like the 3 listed here, end up turning into thermal energy because of various processes. Friction is easily the most common process. If you just take your hands and rub them together, you are transforming kinetic energy in your hands into thermal energy in your hands. As your hands rub across each other, the force of friction between your palms takes some of the kinetic energy from your hands and turns it into thermal energy that's now inside of your hands, because the entire purpose of friction existing is just to take kinetic energy away from stuff and turn it into thermal energy. And this is why friction always makes things warmer. The purpose of friction is to turn mechanical energy into thermal energy, and that's why machines tend to overheat eventually, like your car engine. It's got a lot of moving parts in it. There's a lot of explosions going on inside of your car engine. All those processes, because of friction, create thermal energy, and that's why the engine gets really, really hot. That's why if it doesn't have a good cooling system, it'll overheat and melt. So, thermal energy is going to be the primary focus of these first 3 chapters of this class and the first test. Now, when an object possesses thermal energy, it gets warmer. So if you touch something and it feels hot, what you're feeling is thermal energy entering your body. And when an object possesses thermal energy, its particles become literally more energetic. it's a common expression that when you feel energized, you feel energetic, you're moving around, you're thinking about motion, you're getting up and doing stuff. And thermal energy is quite literally like that, just on the subatomic level. When matter possesses thermal energy, that matter is literally energized. All of its atoms, all of its particles, I'm using my hand as an example. If thermal energy is added to the palm of my hand, then all of the atoms that make up my hand will be more energized. They'll be moving around a lot more. They're going to bounce off of each other. They're naturally going to end up spacing apart because they have this energy. Meanwhile, if something has less thermal energy, so say I used this hand to touch something that's hot, so now this hand has more thermal energy in it than it's supposed to. If I use my other hand to touch something cold, this hand will have less thermal energy in it than it's supposed to. And when something has less thermal energy than is needed, its particles literally have less energy. They're not going to be moving around as much. They're not going to be bouncing off of each other as much. And so the difference here between what happens at the subatomic level between an object being hot or an object being cold, this is what creates the physical phenomena of temperature. Already talked about these points a little bit. In a hotter substance, the particles are naturally bouncing off of each other more, so there's more collisions on the subatomic level. That's what this slide is referring to. Collisions result in work being done, and so yeah, on the previous slide, this represents when, say, the palm of your hand has thermal energy in it and it's hotter than it's supposed to be, then your particles in that hand are bouncing around more than they normally would. They're bouncing off of each other. They're energized. They're moving around at high speeds. And because of that, they literally tend to bounce off of each other more often. It's like turning on a fan inside of a gumball machine. There's energy and all the gumballs are going to start bouncing all over the place inside of the machine. And because these particles are bouncing around more often, they literally collide with each other more often, those collisions between the various subatomic particles result in work being done, because the particles will exert forces on each other as they move together and move apart. And that work between the colliding particles is the reason why thermal energy can transfer between one object to another. Say, for instance, if you'll recall, well, talking about any sort of a collision in Physics 1510, if you have two objects moving together and colliding, there's going to be an exchange of energy between those two objects. Your atoms colliding is the same thing, except when atoms collide, they exchange thermal energy. So when you touch something that's hot, your particles are literally colliding with the particles of the hot object, and its molecules, which are moving around very fast, will hit your molecules, which are moving around pretty slow, and in those collisions, there will be an exchange of energy that causes thermal energy to go from the hot thing and into your hand. So this is the mechanism by which thermal energy is transferred between objects. Now that said, there's actually 3 different ways that thermal energy can transfer between multiple objects. And the method I've been describing so far, where one thing is just touching another thing, and there's collisions of particles between the two touching objects, that is called conduction. Thermal conduction is what happens when two things touch and thermal energy flows between them. And this happens every single time you touch anything ever. Whenever two objects touch, there will be an exchange of thermal energy between them, automatically, inherently. Because if you're touching something, your particles are going to be able to collide with that object's particles. You can't avoid it. And in those collisions, energy is going to be exchanged. The energy will automatically flow from the hot object into the cold object. So whenever two things are touching, and we call this state being in thermal contact, there will be conduction between those objects. If you touch something that's hot, thermal energy will conduct from the hot thing into you. If you touch something cold, thermal energy will conduct out of you and into the hot object. Sorry, rewind, I misspoke. If you touch something colder than you, that makes you the hot object, thermal energy will transfer out of you and into the cold object. Thermal energy always conducts from hot to cold. So it's worth keeping in mind that heat is the presence of thermal energy, whereas coldness is the absence of thermal energy. It's worth keeping in mind. So, conduction is by far the easiest, most straightforward way that thermal energy can flow between two different objects. They just touch and thermal energy transfers direct through the contact between them. There is also two more ways besides that. We'll talk about them briefly because they'll come up from time to time. The second method is through convection, and this is how your oven works, basically. Say you were to put a Thanksgiving turkey in your oven and you want it to cook. So you turn the oven on, the turkey's in the oven, and the turkey will be warmed by the oven. If you've ever looked inside of an oven while it was on, you've probably noticed heating coils on the top or the bottom, or probably both. And those coils are what heats up. But notice that the turkey's sitting in the middle of the oven, whereas the heating coils on the bottom aren't touching the turkey. There's no direct contact between the turkey and the coils, which means that thermal energy can't be conducting from the coils into the turkey because there's no direct thermal contact. Instead, the way that ovens work is via convection. The coils on the bottom aren't touching the turkey, but they are touching the air around the coils. So the air in the oven is going to get hotter. And you might have heard at some point the fact that hot air rises. So air touching the coils is going to get warm, and then that warm air is going to rise to the top of the oven. Well, as it rises, it has to pass and touch the cold turkey. And so that hot air is now touching the turkey, and that thermal energy from the air will transfer into the turkey. That inherently will make the air colder again. It gained thermal energy from the coils, it came up, and it gave that thermal energy to the turkey. Since the air is colder now, hot air rises, cold air sinks. So the now cool air will sink back down to the coils, heat back up, go back to the turkey, heat the turkey, and this cycle will continue for as long as the oven is on. This cycle of air coming up and down is called a convection current, and that's why your oven is probably referred to as a convection oven. You may have heard that term before. And this is how all ovens work. And it's not technically just air that allows this to work. Any fluid can have convection happening through it. Fluids, if you haven't heard the scientific term for this, a fluid is anything that is either a liquid or a gas. Both liquids and gases exhibit fluid tendencies. Solids are the only state of matter the only common state of matter that don't have fluid tendencies. Both liquids and gases have fluid tendencies, which means that both liquids and gases can have convection currents in them. And just like how the air will rise and fall in the oven, the same thing happens in a pot of boiling water. You put a pot on the stove, it absorbs heat from the heating coil beneath it, that heat enters the water, hot water will rise, cold water will fall, and you get these currents in the pot of water that cook your pasta. So convection is really just conduction with extra steps. For conduction, object A and object B are touching. For convection, object A and object B aren't touching, but some fluid medium between them allows heat to go up from the bottom. One weird quirk of convection, well, actually two quirks of convection are, you need a fluid medium, you require to have a fluid medium, there needs to be air or water or something like those things present for it to work. It doesn't work in the vacuum of space. The other thing is, it also only ever carries heat upwards. Convection can never bring heat down because it depends on the hot air rising, on the hot water rising. This is why the hottest place to be at the bonfire is standing directly over the fire. The hot air is constantly rising away from the flames. But if you're off to the side, or even somehow under the fire, it won't feel hot because the hot air only ever goes up. So convection can never heat something beneath the hot object. The last method of heat transfer is radiation, and this is the method through which Earth is warmed by the sun. The Earth and the sun are very far apart. They're not touching directly, so heat does not get from the sun to the Earth via conduction. There's no direct contact between the two. There is also no fluid medium between the sun and the Earth because there's no air, no water, no fluid at all in the vacuum of space between our planet and that star. So instead, the sun is constantly radiating light and other forms of radiation, and that radiation is just shooting out in all directions. And when radiation, including light, from one source hits something else, that light is absorbed by the object that it hit, and that object gains thermal energy from the light. This is the reason solar panels work. Solar panels are designed to absorb energy from light radiation and turn it into electricity. On an even simpler basis, this is why you just feel warmer in direct sunlight. It could be a sweltering summer day, and the air could be the same temperature all around you, but you will always feel hotter in light than you will if you were under the shade of a tree. That's because if you are being hit by light, you're absorbing energy from radiation, and you're absorbing thermal energy from the radiation. So these are the three different ways that thermal energy can move from one object to another. We're primarily going to be focusing on conduction because it's easily the most straightforward, and it's the one that you tend to think about most on your daily basis as a human being on planet Earth. But convection and radiation will come up from time to time, so it's worth remembering they exist. Now, I mentioned before that thermal energy always flows from hot to cold. Thermal energy, think of it kind of like osmosis in a cell. If you have a lot of water in one place and no water in the other, all of that water wants to go where there's no water. A lot of my students are either biology students or chemistry students. So in comparing it to a biology example, if a cell is submerged in pure water, there's more water concentration out of the cell than in the cell, and so water will start to transfer into the cell to make the ratio of water to not water the same on either side of the cell barrier. And it's the same with thermal energy. If two things are touching, thermal energy will continue to flow from hot to cold until the two temperatures of the two different objects equalize. So I have here some ice water. If I was to stick my finger in my ice water here, I'm at a warmer temperature than ice water is. Therefore, if I touch my ice water, thermal energy will exit my body and enter the ice water. And that process would continue until I and the water are at the same final temperature. As long as we're at different temperatures, we have different amounts of thermal energy across my mass versus the water's mass. And thermal energy will keep transferring as long as I'm touching the water and as long as there is a temperature difference. Any two objects that are touching, thermal energy will transfer between them, specifically from hot to cold. Heat always flows from hot to cold, since heat is the presence of thermal energy and cold is the absence of thermal energy. If two things are touching, thermal energy will always flow between them until their temperatures equalize. So if you touch something and you feel any temperature at all, that means that whatever you're touching is at a different temperature than you, and there is a flow of thermal energy until it reaches the same temperature as you. Now, it's worth considering human beings don't actually have thermometers in their skin. You don't specifically have any method of telling what something's temperature is. You can't touch something and say, yes, this is exactly 32.4 degrees Celsius. You do not have a built-in thermometer. All your body is capable of detecting is whether or not thermal energy is entering you or exiting you. If something feels hot, that means its thermal energy is entering your body as you touch it. If something feels cold, thermal energy is exiting your body as you touch it. And how hot or how cold it feels is really just a gauge of how quickly the energy is either entering you or leaving you. If something is relatively the same temperature as you, then the energy's not going to move all that fast. Whereas if I touch dry ice, which is extremely cold, thermal energy will exit my hand incredibly fast, and that will create the sensation of very, very cold. Same thing if I was to touch, don't recommend this, red hot metal, a lot of thermal energy would enter my hand very quickly, and that would feel very hot. Whereas if I'm touching something that's the same temperature as me, there would be no net energy flow. Therefore, I wouldn't actually detect any change in temperature. Because, again, you don't have a built-in thermostat. You just have the ability to detect the speed at which thermal energy exits you or enters you. It's worth keeping in mind. We will actually talk about this statement later. We're going to do a separate chapter about the laws of thermodynamics. We'll talk about this statement a little bit later. I apologize. Let's now talk a little bit about the actual math behind temperature calculations and what temperature actually means. So, as I said, humans do not have built-in thermometers. We did not invent the measurement of temperature simply by touching things and just knowing what temperature they're at. We had to invent all of our temperature scales through a slightly different means. Now, what temperature means is it is specifically a measurement of the average kinetic energy level of the atoms or molecules that make up a substance. So, in general, if something is at a higher temperature, its atoms have more thermal energy. That means its atoms are going to be moving around a lot more. They will have more kinetic energy. Secretly, thermal energy is actually kinetic energy, but on the subatomic scale, because it's the motion of subatomic particles with mass. Temperature is a measurement of the average energy level of the particles in a complete whole object. So, say I'm comparing my own body to my ice water. My own body is warmer than the ice water, so if you were to randomly take one of my atoms and one of the water's atoms, my body's at a higher temperature, so the atom you pulled from me would have more energy than the atom you pulled from the ice water. Temperature is simply a numerical representation of that comparison. You're comparing the energy level of one atom between each object that you're comparing. Temperature exists as this comparison, and it's not even a good measurement of the total energy level an object has. It's simply a measurement of its average energy level. We'll get more into what that means a little bit later. For right now, keep in mind that temperature represents the average kinetic energy level of a specific subatomic particle within a specific material. And there's a formula on screen here that does show that fact. What I'm currently tracing around is the original classic formula for kinetic energy. Kinetic energy equals 1/2 times the mass of an object times its velocity squared. And like I said, thermal energy is secretly kinetic energy, but on the subatomic level. So this formula still actually works on the subatomic level. You can use this to determine the kinetic energy of, a hydrogen atom if you knew its mass and you knew its velocity. Now, knowing the mass and the velocity of atoms is really hard. So some very smart people created a slightly different version of the formula that says the kinetic energy level of a single atom of a substance is equal to 3/2 times K, which is this constant down here. So if you ever need to use this formula for anything, the K refers to this constant, it'll always be this number, times the temperature of the object. This tells us directly that if something's temperature is higher, the atoms in it have more kinetic energy. So that tracks with what we've been talking about so far. So, considering that formula, we don't really have a good way to determine the energy, like the exact kinetic energy of single atoms. So to create our temperature scales and to actually measure temperature, humans had to get creative and create other scales, other processes through which to actually measure it. And there's 3 common machines that we use to determine temperature over the years. Thermometer is the one you hear about most often. Usually it's got some liquid in it that you can see increase and decrease in size as it changes temperature. Thermometer is just the classic means that we use to determine temperature. But electronics have 2 other ways of doing it that have been invented within probably the past couple hundred years or so. If you hear the term thermistor or thermocouple, those are just 2 different electric mechanical ways to measure temperature. They're basically just electric thermometers. The thermostat in your house likely uses a thermistor or a thermocouple instead of a classic liquid thermometer. So, humans, if you were to touch an object, you do not have a built-in thermometer to tell you what the temperature of the thing you just touched was. So humans had to create temperature scales at different times throughout history. There's most commonly 3 temperature scales that come up on a regular basis that we're going to address in this class. And we're going to talk about them in the order they were invented. The very first temperature scale ever invented was the Fahrenheit scale, which is the one we use in the United States, for better or worse. And it was invented by a man named Gabriel Fahrenheit. And I believe that he was from a northern European country, a very cold place. And the Fahrenheit scale is kind of infamous in the international and scientific communities for just being really weird. The freezing temperature of water at 32 is... in Fahrenheit, the freezing temperature of water is 32 Fahrenheit, and the boiling temperature of water is 212 Fahrenheit. It was the first scale invented, though, and so for a long time, the Fahrenheit scale... maybe not a long time, but for a while, it was the only temperature scale that existed. Gabriel Fahrenheit was the first person to properly invent one. And that's why the Fahrenheit scale is probably still used in some parts of the world, because it was the first one, and some people just got used to it and never bothered changing. And it's not used so much in academic circles these days. There's 2 other scales that work better for academia. If you've ever looked at the Fahrenheit scale and thought it was weird, freezing water at 32, boiling point at 212, these standards are kind of arbitrary. It's said that Gabriel Fahrenheit developed this system using very specific equipment, and he literally was just taking basically a marker on his test thermometer and just marking off various intervals and just applying numbers to them that made sense to him. And I'm sure it made sense to him, but freezing and boiling being 180 degrees apart and specifically freezing happening at 32 seems kind of weird to the rest of the world. It's said that one of the reasons for this weirdness is that he wasn't using fresh water. He was using salt water, frozen salt water, basically. The legend goes he was from a northern European country, and he was doing most of his experiments with frozen salt water that he dredged off of ships in a shipyard. And salt water has slightly different freezing and boiling properties than fresh water does. So Gable Fahrenheit made the first temperature scale. It was the only one we had for a while, and even though it doesn't always make total sense, it's all we had, and that's probably why America still uses it. It was the one that had been used, and why would they bother changing? Not much longer after Gabe invented the Fahrenheit scale, though, a different man named Anders Celsius invented the Celsius scale. And the reason he did that is very specifically because the Fahrenheit scale is kind of weird, and he wanted a more regular, more uniform scale to use instead. So Anders Celsius invented his own temperature scale, the Celsius scale, and he specifically made his scale set in base units of 10. He set on his scale the freezing point of water at 0, the boiling point of water at 100, and after testing the water at all the other temperatures, he filled in all the blanks from there. So he got his baseline in from this thesis statement here, and all his other research was finishing the scale from that point. And the Celsius scale, because it's base 10, because everything is spaced at even intervals apart, it became widely adopted by the scientific community across the entire world. So a lot, for hundreds of years, scientists used the Celsius scale almost exclusively, because mathematically it was just a lot smoother and a lot cleaner than the Fahrenheit scale. And Celsius became the golden standard in scientific communities and in a lot of countries around the world for a long time. And it probably would have stayed that way if it weren't for the fact that we discovered the concept of absolute zero. If you think about it, 0 Celsius, or 32 Fahrenheit, is not the coldest temperature that exists. You can get colder. It doesn't happen a lot on PC campus, but it gets below freezing. You can have days that get down to 30 Fahrenheit or 25 Fahrenheit. And if you translate that into Celsius, you would have temperatures lower than 0, sub-zero temperatures. So the freezing point of water is not the coldest point that exists. You can get far colder in the dead of winter, in the Arctic or the Antarctic circles, on Pluto, which is just, a frozen ball of ice and rock. Things can be colder than 0 Celsius, and so some scientists realize that setting the freezing point of water as 0 is not actually the best thing to do academically, because 0 should apply to the coldest temperature that really exists. And that coldest temperature, we call it absolute 0 because you can't get any colder, it turns out to be about negative 273 Celsius. I think in Fahrenheit it's about negative 414 Fahrenheit. It is the coldest temperature that can possibly exist. Absolute 0 is the point where an object has no thermal energy. To get something to absolute 0, you have to pull all the thermal energy out of it. And since its particles don't have any thermal energy, its particles are not moving anymore. Even the particles of ice move around a bit because they still have some amount of thermal energy. The fact that ice can exist at 0 Celsius but can still get colder means that you can keep taking thermal energy out of it until you hit absolute 0 and there's no more energy left to remove. And at that absolute 0 point, when there's no energy left, its particles are just stuck, frozen in time, completely immobile. It's a surreal experience that doesn't actually happen in nature because of just the chaos of the universe around us. But even though it doesn't happen, we still have to acknowledge it as the real zero, as the coldest thing that can exist. And so, keeping in mind that absolute zero is really the coldest thing, a third scientist, a person named William Thomson, but whose title was Lord Kelvin, I'm going to assume it was some sort of European nobility, developed the Kelvin scale. And what Lord Kelvin did was he took the Celsius scale, because it was the scientific scale at the time, it's the scale most scientists were using, and modified it into the Kelvin scale. The Fahrenheit and the Celsius scale are completely separate. There's 100 degrees between freezing and boiling Celsius. There's 180 degrees between boiling and freezing Fahrenheit. Fahrenheit and Celsius are completely different. But Kelvin is directly based on Celsius. Literally, if you want to convert Celsius into Kelvin, you just need to add 273. Alternatively, if you're converting from Kelvin to Celsius, you need to subtract 273. So the Celsius scale and the Kelvin scale are basically the same thing. They're just offset from one another. Now, all three of these scales, as different as they are and all the different reasons they were invented, they all still measure the same thing. They measure temperature. They measure the average energy level of something's particles. And that means that converting between them is the same as converting between feet and meters. It's the same, you're measuring the same thing, it's just a different benchmark. And so what you can currently see on screen is just a comparison of various temperatures in all three scales. For example, the freezing point of water on the bottom line here, 273 Kelvin is the freezing point of water. That corresponds to 0 Celsius. That corresponds to 32 Fahrenheit. Up here on this line is the boiling point of water. That's 373 Kelvin, 100 Celsius, and 212 Fahrenheit. And this should give you a good idea, a good representation of the fact that kelvins and Celsius are really the same thing, because it shows here that there's 100 numeral difference between freezing and boiling in both scales. Literally, the Kelvin scale is the Celsius scale with 273 added to it, just to offset 0 down to absolute 0. Which means that Kelvin and Celsius can sometimes just be completely interchangeable because their units are the same size. Fahrenheit is the real odd man out here because its units are a different size. It is 180 degree separation between freezing and boiling. So it's the one that's the most incompatible with a lot of the formulas in this class. All right. So, since the scales all measure the same thing, you can convert between them. Let's just talk briefly about those conversion formulas. This formula here, TF equals 9/5 times TC plus 32 degrees. This is the conversion from Celsius into Fahrenheit. If you have a Celsius temperature and want a Fahrenheit temperature, you can put the Celsius number right there. You multiply it by 9/5, and then you add 32 to that product, and that's the Fahrenheit version. Subsequently, you can use the same formula to convert a Fahrenheit into a Celsius. If you plug a Fahrenheit in and leave your Celsius as an unknown, you'd want to subtract 32 over to the left side, and then divide both sides by 5/9. If you wanted to write that out as a separate formula, that would look like TC equals 9/5 times open parentheses. Nope, I misspoke. My apologies. TC equals 5/9, open parentheses, TF minus 32, closed parentheses. The conversion between Celsius and Kelvin is a lot more straightforward. If you have Celsius, you literally just add 273 to it, and that will give you Kelvin. Subsequently, if you have Kelvin and want Celsius, you can subtract 273 from the Kelvin to get Celsius. Some things to note. again, since kelvins and Celsius are the same size, delta K is equal to delta C. If you have a change in temperature in the Celsius scale, it will be the same number as the change in the Kelvin scale. For example, if you increase from 0 Celsius to 25 Celsius, that's a delta C of 25. The delta K would also be 25. And that means that if your formula has a change in temperature in it, Kelvin is the official unit, metric unit for temperature. So most of the formulas are designed to work with Kelvin. But if the formula has a delta temperature in it, if it's specifically asking for the change in temperature, then either Kelvin or Celsius will work, since delta Kelvin is the same as delta Celsius. I'll try to point out when this factor comes up in each of our formulas. Kelvin is always your safest bet in this class. If a formula asks for temperature, it's always safest to put Kelvin in there, just as a general rule. But there will be times that if you're given a Celsius temperature, you'll be able to keep it in Celsius and get away with it. I'll try to bring those up as we get to them. And to start with, just as some brief practice, here we have 45 units of each temperature scale, and we're just going to talk briefly about what each of these look like in the other two scales. One thing to quickly note is, for reasons I don't have a very good explanation for, the units are degrees Celsius, degrees Fahrenheit, and then just kelvins for the Kelvin scale. There is no such thing as a degrees Kelvin. They're just called kelvins. There's no little degrees unit there. It's just kelvins. I was never told a good reason why that is. Maybe Lord Kelvin just insisted upon it. So here we have 3 different temperatures. I'm going to show the answers in a minute to what these would be converted into the other two scales, and I'm going to show my work over here on the side. Before that, I just want you briefly to look at each of these and ponder for a moment if 45 is hot or cold in each of these scales. So if you think about 45 degrees Celsius really quickly, is that hotter or colder than what you would normally experience? Then think about 45 Fahrenheit. Is that hotter or colder than your usual baseline temperature as a human on Earth? And then lastly, 45 Kelvin. Is that hotter or colder than what you normally experience? And if you're following along with these slides, the answers and my work are on the next slide, shown here now. 45 Celsius is actually pretty hot. 25 Celsius is considered to be about room temperature. So odds are, I assume the room you're in is somewhere between 70 to 75 Fahrenheit. That corresponds to about 25 Celsius. 45 Celsius is then about 113 Fahrenheit and 318 Kelvin. So 45 Celsius is hot. Pretty hot for a human. 45 Fahrenheit, meanwhile, is colder than what you usually experience in a building, at least. That's considering that about 75 Fahrenheit is usually room temperature. 45 Fahrenheit is pretty good on your way down to freezing already. Freezing in Fahrenheit is 32. So it's pretty cold. That's going to translate to 7.2 Celsius and 280.2 Kelvin. I've got my work for these shown over here. The last one is 45 Kelvin. And considering that 0 Kelvin is absolute zero, and that's the coldest temperature that exists, 45 Kelvin is pretty close to absolute zero, which means it's colder than anything you as a living human will ever experience. If you were ever in a room that was 45 Kelvin, you'd be pretty instantly turned into an ice sculpture. 45 Kelvin correlates to negative 228 Celsius and negative 378.4 degrees Fahrenheit. Again, you'll never experience a temperature that cold, or at least you won't survive. You won't survive a temperature that cold. I've got my work on the side over here. I do recommend you look over this, make sure you're able to replicate these results with the formulas from the previous slides. For all these slides, for all these notes, I'm going to show my work, show my answers for all the sample questions, and talk you through a lot of the logic for them. So, we'll actually talk about that one in the next one. So, temperature is generally how we measure the amount of thermal energy in something, and there's a few different things I want to talk about that relate to the temperature of an object. A few related heat and thermodynamics concepts. The first is a concept referred to as thermal expansion. Now, do you remember from earlier in this slideshow, I'll actually just tab back to show. When we were talking about how objects with more thermal energy, their particles have more energy, those particles are moving around a lot more, they bounce off of each other, and they end up sort of naturally spacing farther apart. As a separate analogy, imagine if a bunch of people were standing still in an auditorium. If a bunch of humans just in a building were not moving, it'd be possible to get them all pretty close to one another. But if all of those people are moving around and pushing off of each other, they're naturally going to end up spacing apart. You're pushing people away. You want people out of your way. They want you out of their way. All these forces as people are moving around will naturally cause just all of the people there to drift further apart. The same is true for subatomic particles when that object has excess of thermal energy. The particles that make something up, if they have thermal energy, they're bouncing around more, they're going to naturally space apart. This is the reason that hot air rises. Hot air, its particles are spacing out a little bit more. Hot air is less dense than cold air. And things float when they are less dense than the fluid they're surrounded in. So hot air rises because hot air is less dense than cold air. Specifically, that hot air expanded due to the concept of thermal expansion. Whenever any material absorbs thermal energy, whenever any material increases in temperature, that object is technically going to grow a little bit. Now, this may not come up a lot in your day-to-day life, but there's one place where there's a few places where people actually do encounter this thermal expansion property of matter. And one of the places that you might have heard it talked about most is actually jewelry, because rings on a human finger tend to change temperature a lot. If you leave your ring off overnight, it's going to cool off in the cool air of your room. Meanwhile, you as a human tend to stay about the same temperature. So in the morning, if you take a cold ring and put it on, you might have a hard time getting it back on because it technically shrank overnight as it cooled down. But after it's been on your finger for a while, and after it's warmed back up by your own body, it tends to expand, and that makes it a little bit easier to slide back off. Maybe you've encountered that before. I've certainly noticed it. All materials do this. Every single material will technically expand when warmed, and that also means that it will shrink when cooled. This also contributes to hot air rising. Again, hot air will expand, and that makes it less dense, so it will float in the colder air. There's another weird place. These two slides represent a demonstration that I will do when this class meets in person. This represents the formulas that I'll talk about briefly in a minute. This picture is, I'm skipping ahead a bit to just show you this picture so that I can talk about it briefly. What this is, you see a car tire here as it drives over this weird metal shape. What this thing is, if you've driven over bridges before, you might have noticed that, spaced every so far apart on the bridge, there were these weird like metal tracks that go horizontally across the road. And a lot of bridges have these. You probably notice the most when on the bridge your car kind of goes ka-kunk, 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 ka-kunk as you're driving across it, as you kind of drift up and down because you're passing over these weird pieces of metal. The reason that those metal pieces are there is because of thermal expansion. When a bridge is installed, it's a big slab of concrete or metal that's just put into place, and its temperature is going to change a lot. It'll get hot in the daytime of the summer. It'll get really cold in the nighttime of the winter. So that bridge's temperature is going to change a lot as the years pass and as the seasons change. That means that bridge is going to repeatedly change size in its bearings, getting bigger as it heats up, getting colder as it shrinks. Those metal pieces are actually designed as gaps. Right now, these gaps are kind of closed. These metal teeth have clunked into each other. This is what the bridge looks like in the dead of summer when it has expanded to its highest degree. But when the bridge cools back down, the teeth are allowed, they have space to separate. But because those teeth are there, you have something to drive over, and it's not just a pothole. The entire reason those things are there is because of thermal expansion. Construction workers, architects, civil engineers have to take thermal expansion into account because those big structures made out of concrete and metal tend to be the ones that expand the most. And you have to factor in that it's going to change size, as the seasons change. Technically, the Empire State Building is only really at its absolute tallest on the hottest day of summer. In the middle of winter, it's technically a little bit shorter. So, everything expands when it's hot and shrinks when it's cold. And we have some formulas to help us determine exactly by how much something will expand or contract. These two formulas here represent the thermal expansion of an object as it gets warmer. We have one version of the formula for expansion in one dimension, just how long something gets because it's heating up. There's a slightly different version of the formula right here for the change in an object's volume as it warms up or cools off. There's two slightly different versions because the numbers for the two different versions do change, but it's still basically the same formula. We're going to look at the length one primarily today, but the volume one will work exactly the same way. The logic we talk about for the length formula today will work for the volume formula when it comes up later. So let's just look at the length expansion formula right here. So what this formula says is an object will change length based on its original length. So the delta L represents the change in length of a certain object, whereas L represents its original length. That change divided by the original is equal to, I'm going to come back to alpha in a minute, is equal to the change in the object's temperature times alpha. What this formula says is the more you change something's temperature, the more it will change size. So notice that if delta T gets bigger, delta L will get bigger. If delta T is smaller, then delta L will be smaller. So if you change something's temperature by a lot, if you heat it up several hundred degrees, it'll get a lot bigger than it would if it was only increasing temperature by 1 degree. So the more you change something's temperature, the more you will change its length. The other term here, this alpha term, this is the coefficient of thermal expansion. And every different material expands at a slightly different rate. Different metals, different rocks, different other types of solids and liquids and gases all expand at slightly different rates just based on what type of materials they are. In general, solids do expand, but not really by a whole lot. Meanwhile, liquids expand more than solids and gases expand more than liquids. Subsequently, that means that gases are also easier to make smaller when you cool them off. For example, say you've ever left a beach ball or a soccer ball out at night. If you leave, beach ball or soccer ball out overnight, it's naturally going to get colder in, the cold of the night. And the gas inside of that ball getting colder is going to take up less space. So the ball might seem like it's deflating, even if it still has the same amount of gas in it, because that gas will take up a smaller volume when it's colder. So if your beach ball seems low, your two options are either inflate it more or try to warm it back up. And since the substance matters, the type of material affects how this formula plays out, this alpha variable right here represents the coefficient of expansion for a specific material. I'm going to tab ahead to a chart right here, and this chart shows the coefficients of linear expansion. That's the alpha from this slide. So length expansion is linear expansion, just getting longer and shorter in one dimension. And so alpha is this list of constants from this table, average coefficient of linear expansion for each of these different types of materials. And looking at this list, we can see that, let's see, on this list, the biggest coefficient of expansion is actually lead. Meanwhile, the lowest one on this table is actually Invar, which most people might not know what Invar is. But next is actually glass. Glass has a pretty low coefficient of thermal expansion, which is one reason why we use glass for a lot of cookware. It resists changing size when you heat it up, which is good. You don't want it growing in a weird way and possibly cracking. Actually, Pyrex has an even lower coefficient, which is good. That's the reason why we make a lot of casserole dishes out of Pyrex. It resists changing size as it heats up, which over time will keep it from breaking. So different materials have different coefficients of thermal expansion based on what they are made of. And this column here represents the alphas in this formula. The other column right here, coefficient of volume expansion, these represent the beta in the volume expansion version. So the volume expansion formula works the same way as the length one. We just swapped out volume for length. Rather than growing in one dimension, you're growing in all three at the same time. And instead of alpha, the coefficient of linear expansion in one dimension, it uses beta, the coefficient of volumetric 3D expansion in all three axes. And so on our table here, there's a different column for the beta values. Every material still has a slightly different one. The alphas and betas are related. Specifically, each beta value is equal to its corresponding alpha times 3. I encourage you to check that over for yourself. Just something to keep in mind. Oh, actually, come to think of it, these materials aren't the same ones as these ones. My apologies. It's not a great table for comparing that. But if you know something's alpha, its beta will be 3 times its alpha. Or alternatively, if you have the beta, divide it by 3, and that will give you the corresponding alpha. So every different material has a different coefficient. And you will always have a table available with these values. You will never need to memorize a single one of them, because there's technically infinitely many of them, since there's infinitely many materials in the universe. I don't have them memorized because that's impossible and foolish. You will always have this table whenever you need it. I promise you. You can use this on your homework. I'll make it available to you on tests when it comes up for a specific question. But whenever we have a thermal expansion problem and we need to know the alpha or the beta for a certain material, you can consult a table like this and just look it up. Let us do a quick sample question just to show this principle in action. Let's say that you measure a length of aluminum pipe with a tape measure. When the temperature is at 21.1 degrees Celsius, you measure the pipe to be 18.700 meters long. If you were to measure that same pipe at this different temperature, 29.4 degrees Celsius, what would its new length be at that temperature? So to work this question, we're going to want to consult our formula for linear thermal expansion. Delta L over original L equals alpha times change in temperature. Now, delta anything, general rule for all physics and math, delta anything is always final minus initial. So delta L is equal to final length minus original length. So original length is actually in this formula twice. In my work here, I've expanded delta L out into L final and L initial. So delta L equals L final minus our initial length, divided again by our initial length. That'll be equal to our alpha. Now, this question tells us the pipe is made out of aluminum. That's our invitation to go over to our table here. Look at aluminum, find the linear expansion coefficient for aluminum, and it's 24 times 10 to the negative 6. And so that would be the number that you plug in for alpha. You can freely consult that table at any time. Then for delta T, that's the change in temperature. Change again is always final minus initial. So our final temperature, 29.4, minus our initial temperature of 21.1. As I said earlier, this is one of those cases where there's a delta T in the formula, which means that delta Celsius and delta Kelvin are both legal here, since the change in Kelvin is the same as the change in Celsius. Now, these are only unknown as length final, so all we have to do now is consult some algebra to get LF equals a number on its own. I recommend you make sure that you're able to get to the correct answer if you're practicing this algebra. That correct final answer is 18.704 meters. That is not a very big change. Our original length was 18.700 meters, and our final length, after heating up by about 8 degrees Celsius, is only 0.004 meters. That is 4 millimeters longer. You likely would not notice that in your day-to-day life. So admittedly, there's only some very specific situations where this will actually be noticeable in your daily existence. So for aluminum, increasing in temperature by about 8 Celsius, there's not going to be a very noticeable difference, admittedly. However, this small increase does get more dramatic at higher temperatures, and it gets more dramatic if the object is longer. If we look at the formula itself again real quick, notice that this is the same formula. I've just taken the L term, the L initial term, and moved it from the denominator of the left into the numerator of the right. So it's the same formula as before, just slightly rearranged. In this form, it's easier to see that if the initial length is already big, the change in length will also get larger. So the bigger the object is, the more it will expand. And so the places where thermal expansion is the most dangerous is in very big or very long objects. This picture currently on screen now is real actual train tracks that were warped because of thermal expansion. What happened here is these rails are incredibly long. They stretch on for miles. And because they're so long and because they're literally attached to the ground, when they expand because of the sun and the summer heat, they don't have anywhere to expand. Like, imagine if this is the railroad track and it's fitted perfectly between my two hands. If it started getting longer, but my hands didn't let it get longer, if my hands didn't give it the space to actually expand, it would eventually just start bowing and bending in any direction that it could. It's like when you take a stick and just cause it to bow upwards. You're expanding it, but you're not giving it space to do it in a straight line. It's going to warp instead. So these rails are longer, but they don't have the space to grow out linearly. So they start warping and buckling, and that can literally cause trains to come down. So this is what happens when something is built incorrectly, when the construction workers, when the architects, the designers don't factor in thermal expansion. When they don't have safety measures like these little, like the teeth on the metal gaps on the bridges. If you don't have a feature like that, you can get serious warping like this. And imagine if this happened instead of long ways across the ground, imagine if it happened to a vertical structure. If something got taller than it normally was, but all of its security features weren't designed to grow along with it, you could have parts of the building cracking off or breaking entirely and the whole thing just falling down just because of a change in the weather. This can get pretty serious, and I want to work another example to show you how serious. So here, this is going to be an example of a bridge that was built improperly. A good bridge has those metal teeth that help allow for thermal expansion to happen. But this bridge, in this hypothetical situation, is going to be a solid piece of steel that does not have room to grow. It's just steel buried between two fixed points. It's going to grow because the temperature is going to rise. Say it was built on a 45 degree Fahrenheit day, and over the summer, that will increase to 100 degrees Fahrenheit. So the bridge is gonna get warmer. That means it's going to expand. Let's say that on this cold day, it was 250 meters long, and that means that the gap that it's spanning is 250 meters long. If it expands, the gap doesn't change size, but the metal bridge will. We're going to treat it as solid steel bridge. The metal's going to get longer, meaning it's not going to fit in this 250 meter gap anymore. It's going to have to buckle and bend and possibly sit at an angle to be able to fit in the same horizontal space because it's not 250 meters long anymore. So the question here is, the question that I'm going to propose to you and show the calculations for, if the bridge was originally 250 meters long on a 45 degree Fahrenheit day, then if it grows up to a certain length on a 100 degree Fahrenheit day, how much higher up is this side going to rise? What I'm envisioning here is if one end of the bridge disconnected, how high up would it go to be able to fit in that 250 meter horizontal gap? And I'm going to show how I calculated this. What I've drawn here as a triangle is basically the right triangle formed by the expanded bridge of the bed of the road and the original 250 meter gap. Because that 250 doesn't change, the size of the gap is going to stay the same, but the bridge is now longer, and the bridge is now going to represent the hypotenuse of this triangle. So this hypotenuse, LF, is the expanded bridge, whereas the bottom leg is the initial length of the gap itself. So this is the metal fit into a gap that's this long. And the trigonometry tells us that in order for it to fit like this, it's tilted at an angle, and there's going to be some change in height on this side. And that change of height is what we want to find out. We want to see how extreme this difference can become. So, first thing I did is I just went ahead and converted Fahrenheit into Celsius because none of the formulas for this class are really going to use Fahrenheit. You might be given Fahrenheit, but you're going to need to be able to convert it into Celsius or Kelvin. So I went ahead and converted 45 Fahrenheit into 7.2 Celsius and 100 Fahrenheit into 37.8 Celsius. Once you have those temperatures, we're going to use the expansion formula here. Delta L over L equals alpha times change in temperature. Like with the previous example, we're solving for L final. Delta L is equal to L final minus L initial. So LF minus 250 divided by 250 is equal to alpha for steel. So the question does say we're going to assume that this is a steel bridge. So we should go back to this table and look up the coefficient of linear expansion for steel. So that's 11 times 10 to the negative sixth. And so that's what we're going to plug in for alpha. Delta T is going to be the change in temperature of the bridge. We want to use our Celsius temperatures here instead of our Fahrenheit ones. So our final is 37.8 and our initial is 7.2. You can use Celsius here or Kelvin here because, again, it's a delta T. That leaves LF, so the same algebra, the same calculation as the previous sample question we looked at. LF will have a final answer of 250.084 meters. And that actually, again, isn't much growth. That would be 8 centimeters longer. Not a whole lot, admittedly. But the trigonometry gets kind of weird here. Because even though the hypotenuse and the base are almost the same length, there's still going to be some height increase here, and we need to figure out what it is. This is the type of thing that civil engineers have to deal with all the time, is figuring out all of these worst-case scenarios that could happen. And since we now know two sides of this right triangle and want the third, this is a right triangle. I forgot to draw the little box right here, but we do have a right triangle here. I'm going to recommend we use the good old-fashioned Pythagorean theorem, a squared plus b squared equals c squared. We could use other forms of trig, but we don't have a number for this angle yet, so this seems to me like the easiest next step. A and B are always the legs of the triangle, so A can be the 250 that we know. B is going to be the other leg, the one that we don't know, so that's going to be what we end up solving for. C is always the hypotenuse, so that'll be the LF that we solved for a minute ago. Note that both of these values are squared, so you have to square them, then subtract 250 squared over, then take the square root of the difference between those two squares. I do recommend checking your work for yourself. Your final answer should be 6.59 meters. And if you're not used to thinking in the metric system, 6.1 meter is it's a little more than a yard. 1 meter is about 3.3 feet. So that would be about at least 20 feet in the air, honestly. Just imagine if your bridge, over time, suddenly rose 20 feet up on one side. That's why this can be pretty serious for big commercial projects like this. Architects have to take this into account, because if they don't, things will literally break and things will collapse because of it. You have to build in safety features, like the teeth in the bridge of the road, or else weird stuff like this will happen and things will disconnect and break off and you'll have bridges falling over. So 8 centimeters longer really can have pretty disastrous consequences depending on how the trigonometry works out. So this type of thing is very useful in specific disciplines. Again, architecture, civil engineering, things like that. So, thermal expansion. It's important. Everything, when heated, will expand, and everything, when cooled, will contract. I have a very cool prop that I will demonstrate in person when this class meets next in person. I just don't have the tools with me right now. It's a really cool demo, though, so do make sure I show it to you. I have the materials on campus. Like I said, everything will expand. This is important, but I don't want to distract from what I was already talking about, so we'll actually address that later. Last thing I want to talk about in this particular chapter, because it ties into other questions on the Chapter 10 homework assignment, is the kinetic theory of gases. Now, when something heats up, it will expand. That's true for solids, that's true for liquids, that is true for gases. And depending on how much chemistry you've taken, this might be starting to sound familiar. When you heat up a gas, it's going to expand. Gases are kind of unique, though, in that they don't really have any definite shape or volume. So if you have a gas sealed inside of something and you heat it up and it has no room to expand, it might instead start exerting more pressure on the walls of its container. And this brings us into the kinetic theory of gases, or as some people call it, Phys1510. This equation, if you've seen it before in chemistry, I'm hoping this is review for a lot of people. This statement is referred to as ideal gas law, and this formula ties up very nicely the relationship between what a gas does based on its temperature, based on its volume, based on its pressure, the pressure that it's under, and based on how much gas there is in a container. So this formula shows all of the different things that can affect the state of a gas. If you heat up anything, including gas, it will expand. But for gas specifically, since it doesn't have a definite volume or shape, other factors that can affect it include how much gas is present. That is the N here in this formula. That represents number of moles of gas. If you don't know what a mole is, it's a chemistry unit that represents, it's a certain number of particles present. So 1 mole of any substance is this many particles, and it's a commonly used chemistry unit. The reason it's in this formula is because if you have more gas particles present, those particles are naturally going to bounce off of each other more and affect the pressure and volume of that gas. Additionally, the temperature of that gas will affect its pressure and volume, because the higher temperature something is, the more it's going to try to expand, and the more it's going to bounce off of its self and its own container. So that will naturally cause volume to rise and potentially pressure to rise. So these two things affect the conjoined pressure and volume of a gas in a sealed container. The purpose of this ideal gas law formula is to compare these 4 concepts of a gas to show how changing one will affect the others. The R term here is a constant, thankfully, so you don't really have to memorize it. This class, you please have formula sheets. There's class formula sheets available to you. You will never be denied your formulas. You don't have to memorize them. Similarly, you don't have to memorize your constants. In the ideal gas law formula, R is a constant. And if you are using units of liters and atmospheres, then that constant is equal to 0.0821. There's some other versions that correspond to other units of pressure and volume, like pascals for pressure or meters cubed for volume. So this is just one possible R constant. You will always have access to whatever R constant you need in a question for this class. So all things expand, but for liquids and solids, temperature is really the end-all be-all of how much something will expand. But for gases, there's these other variables that affect how much it will expand to, that affect what its ultimate volume will be. So as one last sample question for this particular lesson, let's just use the gas law formula to look at the state of a gas as a few details about it change. So let's say that you have 0.75 moles of a gas that is at 25 degrees Celsius in a container with a volume of 1.5 liters. So we know N, we know T, we know volume. We've been asked to find pressure. So if we look at our ideal gas law formula, we know everything but P. So we can plug in our volume of 1.5 liters, our N of 0.75 moles, our R of 0.0821, and our temperature. Now notice in the gas law formula, this T is not a delta T. It's not delta T. And whenever the formula doesn't have a delta T in it, you have to use Kelvin. Delta T, you can use Celsius or Kelvin, but just T, just current temperature, it has to be Kelvin. Which means we need to convert this 25 Celsius into Kelvin. My handwriting is very messy. Please call me out if something isn't legible because of my handwriting. I will fix it. I apologize. 25 Celsius, if we convert that to Kelvin real quickly in the formula, we just want to add 273 to it. That would be about 298 Kelvin. That just leaves pressure as the last thing to solve for, and that gas would be under 12.24 atmospheres worth of pressure. That means it's about 12 times more than the atmospheric pressure that you are currently under just on Earth's surface. But we're also asked, let's say we increase the system's temperature and decrease its volume. What will the pressure on that gas be? So, we'll reuse the same formula, but we're just going to tweak a few values. Our volume is being decreased by 0.25, so our volume is going down. Meanwhile, our temperature is going to increase by 5. Wait, increase by 5. I think I made a mistake here. I subtracted 5. That's my mistake. Temperature's increased by 5. Yes, I made a mistake in my own math, and that's embarrassing. One sec. All right, I fixed the problem. So I accidentally subtracted 5 before, but I was supposed to add 5. My mistake. That has changed my answer a little bit. So, P times 1.5 minus 0.25, end parentheses, equals 0.75 times 0.0821 times the sum of 273 plus 25 plus another 5, end parentheses. That pressure will be equal to 14.93 atmospheres. So it's risen from about 12 and a quarter to about 15. Both of the changes made, the reducing of volume and the increase of temperature, are ones that will increase the pressure. If you decrease the volume that a gas has to exist, it's naturally going to press back harder against the wall of its container. Say if you take a balloon and you squeeze inwards on it, the pressure inside the balloon will go up, and that's a very easy way to get the balloon to pop because of the increased pressure. Similarly, if you increase the temperature of a gas, but it doesn't have anywhere to expand, its particles are naturally going to bounce around more, bounce off of each other more, bounce into the wall of their container more. And as a result of that, that will also increase the pressure. So both of the changes made in this part B increase the resulting pressure inside of this particular vessel. Now with that, and this is just a formula from earlier. So with that, that is all the material that is sectioned off as Chapter 10 for this particular class. Please do go back over this video as you study this particular chapter. You don't have to watch it all in one sitting. This is material for you to be able to peruse at your leisure, at your discretion. You can jump into our class calls, and I will happily give more examples and elaborate on any part of this. You do not have to absorb all the information just from this video. The point of the video is so that you have something you can watch at any time, something that you can use however it benefits you. And then the calls are for you to be able to ask me any questions, seek out any elaboration, seek out any help possible. I'll go over any of this again, slower, using different examples, whatever you need. But that's everything that is officially labeled as Chapter 10 content for this class. So all of the formulas here, all the concepts here are the things that you would need to be able to do the Chapter 10 homework for this class. So we're going to average about one chapter a week for this particular course. So I recommend using the material from this to look at the Chapter 10 homework, make sure the things within it make sense to you, make sure you're able to use the formulas, and over the space of the week, make sure that you're able to finish up that homework, finish up the related quiz, and then next week we will move on to Chapter 11 content, which will refer back to this and make use of it. Again, ask me literally any question. literally anytime, both in our class calls, but also via email. I will help you any time of day. And see you soon. Have a wonderful day.